In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about general relativity and also the Ricci inverse gravity. In the subsequent sections, we first examine the scalar perturbations of modified black hole solutions and then investigate the Hawking temperature. We analyze how the modifications introduced by the gravity theories affect these quantities and compare the results with those predicted by general relativity, highlighting the shifts and deviations caused by modified gravitational frameworks. The third sections talk about scalar perturbations and effective potential QNMs. In this section, we investigate the perturbations of a mass spin zero scalar field by solving the Klein-Gordon equation with the context of the modified gravity theories introduced in the previous sections. The scalar field denoted phi is considered to be massless and its dynamic is governed by the general covariant Klein-Gordon equation. This equation serves as the fundamental equation of motion for a spin zero massless scalar field in a curved spacetime and takes the form given by the 1 divided by square root minus gravitation multiplied by derivative of mu multiplied by square root minus g to the power of micro nu derivative mu phi is equal to 0, where g micro nu is a metric tensor of the space-time and g is its determinant. In the context of modified gravity theories such as FR gravity or Ricci inverse gravity, the background spacetime and the equation of motion can be altered due to modifications to the gravitational action. These modifications can affect the propagating behavior of the scalar field, and we aim to study how the field behaves under the perturbations in these modified frameworks. Given that the background spacetime and is cylindrical, symmetric, and static, we can express the massless scalar field function phi t r phi z as a decomposition in terms of RA R as follows. Phi t r phi z is equal to exponential minus I omega t exponential I m phi exponential I ka z multiplied by R divided by R, where omega is a Q and M frequency. M takes the natural number and K is an arbitrary constant. The modified black hole solutions obtained earlier in the framework of FR and Ricci inverse gravity together can be expressed as the derivative of x to the power of 2 is equal to im divided by 3 or to the power of 2 plus 4m divided by square root minus im divided by 3 or multiplied by the second derivative of time minus second derivative of radius divided by im divided by 3 or to the power of 2 plus 4m divided by square root minus im divided by 3r plus r to the power of 2 df e to the power of 2 minus im divided by 3 r to the power of 2, the second order of derivative of z. Now we calculate determinant of the metric tensor, and it is given by a square root minus gravitation is equal to square root minus im divided by 3 r to the power of 2, where im tends to im to the power of fr as given in equation 2.8 and 2.12, and im tends to im to the power of Ricci inverse as specified in equation 2.21. Which these equations 3.1 can be expressed as f to the power of 2r derivative of r second derivative of r plus fr f in r derivative of r plus omega to the power of 2 minus r to the power of 2 divided by r2. Fr minus divided by r to the power of 2 fr minus ff prime divided by r multiplied by r is equal to 0, where prime denotes ordinary derivative wrtr and l is equal to square root m to the power of 2 minus 3 cos to the power of 2 divided by also f r is equal to minus m divided by 3 r to the power of 2 minus 4m divided by square root minus im divided by 3 r. We now introduce a new coordinate called the tortoise coordinate r star for the modified black hole solutions, defined by dr star is equal to dr divided by fr. And also we have for example, derivative of r star is equal to fr derivative of r. One can rewrite the above differential equation 3.5 as follows: derivative r star to the power of 2r plus omega to the power of 2 minus vr is equal to 0, where the effective potential of the scalar perturbations is given by Vr is equal to n to the power of 2 divided by r to the power of 2 plus f in r divided by r fr is equal to 1 divided by r to the power of 2 multiplied by n to the power of 2 minus 3 cos to the power of 2 divided by im minus 2im divided by 3 and plus 4m divided by square root minus im divided by 3 r to the power of 3 multiplied by minus im divided by 3 r to the power of 2 minus 4m is divided by square root minus im divided by 3r. In the context of our gravity, the effective potential will be VFRR is equal to 1 divided by r to the power of 2 m to the power of 2 minus 3 cos to the power of 2 divided by r minus 16 r to the power of 3 alpha 2 minus 128 to the power of 4 alpha 3 minus 768 all alpha 4 to the power of 5 minus 2 minus 16 to the power of 3 alpha 2 minus 128 alpha to the power of 4 alpha 3 minus 768 alpha 4 to the power of 5 divided by 3 plus 4m divided by r to the power of 3 square root minus r minus 16 r to the power of 3 alpha do minus 128 r to the power of 4 alpha 3 minus 768 4 r to the power of 5 divided by 3 multiplied by minus r minus 16 r to the power of 3 alpha 2 minus 128 r to the power of 4 alpha 3 minus 768 alpha 4 alpha to the power of 5 divided by 3 r to the power of 2 minus 4m divided by r square root minus r minus 16 r to the power of 3 r to the power of 2 minus 128 r to the power of 4 alpha 3 minus 768 alpha 4 r to the power of 5 divided by 3. And the framework of Ricci inverse gravity, it will be such this formulation. Figure 1 illustrates a comparison of the effective potential with general relativity case for scalar perturbations plotted, considering case m is equal to 0 left panel and m is equal to 1 right panel. Here m is 1, I is equal to minus 0.2 and chi is equal to 0.01. Figure 2 illustrates a comparison of the effective potential based on the equation 3.11 with the general relativity case for scalar perturbations plotted considering m is equal to 0 left panel and m is equal to 1 right panel. Here m is equal to 1, I is equal to minus 0.2 and chi is zero point 0.1. From the expressions in equations 3.10 and 3.11, it is evident that the effective potential governing the scalar perturbations is significantly influenced by the coupling constant present in the modified gravitational theories. In the context of all FAR gravity, the effective potential is modulated by the constant alpha 2, alpha 3, and alpha 4, which arise from the gravitational action and the associated field equations. This constant determines the strength and nature of the interaction between the scalar field and the modify the curvature terms, thereby affecting the propagation of scalar fields. Similarly, in the framework of Ricci inverse gravity, the effective potential is influenced by the different set of parameters alpha 2, beta 1, beta 2, and gamma. This constant arises from the specific modification used in Ricci gravity. The interplay between these parameters governs how the scalar field interacts with the modified gravitational background, which affects the dynamics of scalar perturbation in this model. We have generated figure 1, which illustrates the effective potential for scalar perturbation within the framework of FAR gravity, considering various values of the coupling constant. The figure shows how the effective potential evolves with change in the value of the coupling constant alpha 2, alpha 3, and alpha 4. As these constants increase, the potential gradually rises, indicating that the strength of the scalar perturbation is affected by the modifications to the gravitational action. Furthermore, we compare this potential to the standard general relativity case by setting alpha 2 is equal to 0, alpha 3 is equal to 0, and alpha 4 is equal to 0, effectively reducing Fr gravity to the general relativity limit. This comparison highlights the differences between the modified gravity theory and general relativity. In the figure, the red dots lines represents the effective potential and the general relativity case, with the solid colored lines corresponds to the potential in the FAR gravity framework with non-zero coupling constants. The distinction between these two cases provides insight into how the modifications to gravity introduced through the coupling constant alter the behavior of scalar perturbations in a cosmological context. Similarly, in Figure 2, we present the effective potential for scalar perturbations within the framework of Ricci inverse gravity, considering various values of the coupling constants. The figure illustrates how the effective potential changes with the variations in the coupling constants I2, beta 1, beta 2, and gamma. At this constant increase, the potential gradually rises, suggesting that the strength and nature of the scalar perturbations are influenced by the modifications to the gravitational action introduced by this constant. Additionally, we compare this potential with the standard general relativity case by setting alpha 2 is equal to 0, beta 1 is equal to 0, beta 2 is equal to 0, and gamma is equal to 0, which effectively reduces Ricci inverse gravity to the general relativity limit. This comparison emphasizes the differences between the modified Ricci inverse gravity theory and general relativity. In the figure, the red dotted lines represents the effective potential in the general relativity case, while the solid colored line corresponds to the potential in the Ricci inverse gravity framework with non-zero coupling constants. The distinction between these cases provides valuable insight into how the modifications to gravity affect the dynamics of the scalar perturbations in a cosmological settings. These modifications could lead to observable effects that distinguish Ricci gravity and FR gravity from general relativity, particularly phenomena involving scalar field fluctuations, cosmological perturbations, or the behavior of gravitational waves in modified gravity theories. Section 4, vectorial perturbations. Next, we consider the electromagnetic perturbation or spin 1 vector fields requiring the use of the conventional tetrad formalism with a basis E micro to the power of alpha x is established in relation to the black hole metric tensor gravitational micro nu. This chosen basis adheres to the conditions E micro to the power of alpha x, to the power of micro x is equal to delta E by r. Also, we have a E micro to the power of r x, r to the power of nu x is equal to delta micro to the power of nu gravitational micro nu is equal to nu I b e micro to the power of r x e nu to the power of b. Span 1 field is described by the following Maxwell equations: 1 divided by square root minus gravitation multiplied by gravitation to the power of sigma micro multiplied by gravitation to the power of tau nu multiplied by square root minus gravitation, and F sigma t for V is equal to 0. This being one Maxwell field after straightforward calculation yields derivative second derivative of R star E plus omega to the power of 2 minus nu E multiplied by zeta is equal to 0, where the potential has the following explanation from the in general relativity: nu is equal to fr x to the power of 2 r to the power of 2, and also is equal to 1 divided by r to the power of 2 minus r divided by 3 r to the power of 2 minus 4m divided by square root minus r divided by 3r multiplied by m to the power of 2 minus 3 cos to the power of 2 divided by r. In modified gravity theory, we have nu is equal to 1 divided by r to the power of 2 multiplied by minus im divided by 3, r to the power of 2 minus 4m divided by square root minus im divided by 3r multiplied by m to the power of 2 minus 3 multiplied by cos to the power of 2 divided by im to or 4. In the context of the r gravity, the effective potential will be nu a to the power of fr is equal to 1 divided by r to the power of 2 multiplied by minus r plus 16 r to the power of 3 alpha 2 plus 128 r to the power of 4 alpha 3 plus 768 alpha 4 r to the power of 5 divided by 3 r to the power of 2 minus 4m divided by square root minus r plus 16 r to the power of 3 alpha 2 plus 128 alpha to the power of 4 alpha 3 plus 768 alpha 4 r to the power of 5 divided by 3 r multiplied by m to the power of 2 plus 3 cos to the power of 2 divided by minus r plus 16 r to the power of 3 I2 plus 128 r to the power of 4 I3 plus 768 I4 alpha to the power of 5. And in the framework of Ricci inverse gravity, it will be nu e to the power of Ricci inverse is equal to 1 divided by r to the power of 2 multiplied by minus r plus 16 r to the power of 3 alpha 2 minus 3 beta 1 divided by minus 16 beta 2 divided by r minus 4 gamma divided by r to the power of 2 divided by 3 r to the power of 2 minus 4m divided by square root minus r plus 16 r to the power of 3 alpha 2 minus 3 beta 1 divided by r minus 16 beta 2 divided by r to the power of 2 minus 4 gamma divided by r to the power of 2 divided by 3 multiplied by r multiplied by m to the power of 2 plus 3 cos to the power of 2 divided by minus r plus 16 r to the power of 3 alpha 2 minus 3 beta 1 divided by r minus 16 etc. divided by r to the power of 2 minus 4 gamma divided by r to the power of 2. From the expression in equation 4.6 and 4.7, it is evident that the effective potential governing the spin 1 vector perturbation is significantly influenced by the coupling constant present in the modified gravitational torus in the context of FR gravity. The effective potential is altered by the coupling constant I2, I3, I4, which arise from the functional form of the gravitational action and the associated field equation. These coupling constants determine the strength and nature of the interaction between the vector field and the modified curvature terms, thereby affecting the propagation of scalar fields. Similarly, in the framework of Ricci inverse gravity, the effective potential is affected by a different set of coupling constants alpha 2, beta 1, beta 2, and gamma. These constants arise from the specific modifications used in Ricci inverse gravity. The interplay between these parameters governs how the spin-ball vector field interacts with the modified gravitational background, which affects the dynamics of scalar perturbation in this model. Figure 3 illustrates a comparison of the effective potential 4.6 with general relativity case for the vector perturbations plotted considering case m is equal to 0 left panel and m is equal to 1 right panel. Here m is 1 and I is equal to minus 0.3 and chi is 0.1. Figure 4 illustrates a comparison of the effective potential 4.7 with general relativity case for vector perturbations plotted considering m is equal to 0 left hand and m is equal to 1 right hand. Here m is equal to 1, I is equal to minus 0.3 and chi is equal to 0.1. In figure 3, we illustrate the effective potential for electromagnetic perturbations within the framework of FR gravity, considering various values of the coupling constants. This figure demonstrates how the perturbation's potential alters with change in the values of the coupling constants alpha 2, alpha 3, and alpha 4. As this constant increases, the potential gradually rises, indicating that the strength of scalar perturbations is affected by the modifications to the gravitational action. Furthermore, we compare this potential to the standard general relativity case by setting alpha 2 is equal to 0, alpha 3 is equal to 0, and alpha 4 is equal to 0, effective reducing FR gravity for the general relativity limit. This comparison highlights the difference between the FR gravity theory and general relativity. In the figure, the red dot lines represents the perturbation potential in general relativity case, while the solid color lines correspond to the potential in the FR gravity framework, which non-zero coupling is constant. Similarly, in figure 4, electromagnetic perturbations potentials within the framework of Ricci inverse gravity considering various values of the coupling constant is generated. The figure illustrates how the effective potential changes with the variations in the coupling constant alpha to beta 1, beta 2, and gamma. As these constants increase, the potential gradually arises, suggesting that the strength and nature of the scalar perturbations are influenced by the modifications to the gravitational action introduced by this constant. Section 5, effective of GUP and quantum tunneling of scalar particles in FR and Ricci inverse gravity theories. Hawking radiation is a quantum mechanical phenomenon that arises near the event horizon of a black hole. Modifications to the standard Hawking radiation inspires the generalized uncertainty principle or GUP, provide a window into the interplay between quantum mechanics and gravity. The GUP or generalized uncertainty principle modified Calan-Gordon equation is a central tool for exploring these corrections. In this section, we calculate the generalized uncertainty principle, modify Hawking radiation of cylindrical black hole described by two metrics in FR gravity and Ricci inverse gravity To this end, we employ the quantum tunneling approach and solve the generalized uncertainty principle modified wave equation for scalar field propagating in these backgrounds. However, since both metrics of those modified gravity theories are structurally identical to each other, we consider equation 2.22 as a generic line element of cylindrical black hole of cosmological constant R. Then we shall replace R with Im to the power of Fr 2.12 and Im to the power of Ricci inverse 2.20 respectively. The generalized uncertainty principle Kg for square free theta is given by the reference 100 minus IH to the power of 2. The second derivative based on the t theta is equal to IH to the power of 2 derivative I and derivative of I plus mp to the power of 2 multiplied by 1 minus 2 alpha generalized uncertainty principal multiplied by ih to the power of 2 derivative to the power of the second derivative of I derivative of I plus mp to the power of 2 where alpha generalized uncertainty principal is the GUP parameter and MP is the mass of the scalar particle. The above equation includes quantum gravitational correction due to the GUP and will be used to derive the corrected Hawking temperature. To solve the GUP Kaji, we assume the following wave function for the scalar field as this equation where STRFZ is the action expressed as follow is equal to minus ET plus WR plus JP plus KZ plus K. Here is the energy. J represents the angular momentum. K denotes the separation constant associated with the z direction, and K is a complex constant. Substituting theta into the KGE and retaining only the leading order terms in H, we obtain this formulation. After substituting on stars in equation 4.4 and focusing only on radial motion, j is equal to 0, k is equal to 0, and substituting, the equation can be simplified to these equations. 1 divided by gtt multiplied by e to the power of 2 is equal to grr multiplied by w prime r to the power of 2 plus mp to the power of 2 multiplied by 1 minus 2 alpha GUP or generalized uncertainty principal multiplied by GR multiplied by W prime R to the power of 2 plus MP to the power of 2. Recognizing and solving for W prime R, we get W prime R is equal to positive negative square root e to the power of 2 divided by GTT minus MP to the power of 2 multiplied by 1 minus 2 alpha generalized uncertainty principal MP to the power of 2 divided by GRR multiplied by 1 minus 2 alpha GUP MP to the power of 2, which naturally yields the following integral solutions for WR. WR is equal to positive negative integral square root e to the power of 2 GTT minus MP to the power of 2 multiplied by 1 minus 2 alpha GOP MP to the power of 2 divided by GR 1 minus 2 alpha GOP MP to the power of close to the horizon RH where GTT is equal to 0 and the metric function delta R is equal to GTT can be expanded as these formulations. To compute the imaginary path around the pole, we employ the Feynman's prescriptions method and performing some manipulations, we obtain IMWR is equal to positive negative PR divided by square root delta P RH multiplied by 1 minus 2 MP to the power of 2 alpha generalized uncertainty principle. The designation of a negative positive sign denotes an ingoing outgoing bosons. It is pertinent to acknowledge that the well-known issue of the factor 2 discrepancy present in the aforementioned expression, which result in an incorrect estimation of the tunneling rate, can be rectified through a method delineated in. Alternatively, this issue can be addressed by assigning a probability of 100% to the scenario involving incoming bosons. Specifically, we express this as P negative is almost equal to e to the power of minus 2 IMW minus is equal to 1. We consequently result in IMS minus is equal to IMW minus plus a cup multiplied by is equal to 0. Conversely, considering the bosons being emitted, we observe that IMS plus is equal to IMW plus K. Based on equation 516, it becomes evident that the W plus is equal to minus W negative. Consequently, the tunneling probability associated with the emitted bosons can be interpreted in the following manner. P plus is equal to e to the power of minus 2 IMS plus almost is equal to e to the power of minus 4 IMW. Figure 5 demonstrates the influence of the generalized uncertainty principal parameter alpha GUP and the coupling constant I2, alpha 3, and alpha 4 on the modified Hawking temperature of generalized uncertainty principal to the power of FR for cylindrical black holes in FR gravity. The plot includes two scenarios: alpha generalized uncertainty principal is equal to 0, no GUP corrections, and alpha GUP is equal to 10. MAP is equal to zero point 0.1 with GOP corrections, allowing for a direct comparison of quantum gravity effects. The Hawking temperature decreases as the cosmological constant approaches zero, highlighting the suppressive effect of alpha GOP in the black hole evaporation rate. High values of alpha 4 further amplify the deviation in TGUP to the power of Fr from general relativity, underscoring the significant role of higher order curvature corrections in FR gravity. On the other hand, Figure 6 illustrates the distinct thermodynamic behavior of cylindrical black hole in Ricci inverse gravity under the influence of the generalized uncertainty principal parameters alpha GUP and coupling constant alpha 2, beta 1, beta 2, and gamma in the general relativity limit, where alpha GUP and Ricci inverse parameters are all set to 0. The Hawking temperature T GUP to the power of Ricci inverse vanishes as all tends to 0, indicating complex black hole evaporation. However, when Ricci inverse gravity is switched on, the Hawking temperature remains finite even as all approach zero, strongly suggesting the formation of black hole remnant. Underscores the non-trivial contributions of the Ricci inverse gravity parameters to the black hole thermodynamics. Additionally, the inclusion of generalized uncertainty principal corrections further modify the evaporation profile, highlighting the interplay between the quantum gravity effects and the modifications introduced by which inverse gravity. The observed deviations from general relativity are amplified by higher order curvature corrections governed by alpha 2, beta 1, beta 2, and gamma. In summary, the analysis of generalized uncertainty principle modify Hawking temperature for cylindrical black holes in FR gravity and Ricci inverse gravity reveals significant quantum gravitation correction, specifically the coupling constant alpha 2, alpha 3, and alpha 4 in FR gravity towards significantly alters the GOP correct Hawking temperature, modifying the black hole evaporation rate compared to that in general relativity. Similarly, in context of Ricci inverse gravity theory, the two coupling constants alpha 2, beta 1, beta 2, and gamma were shown to significantly affect the GOP corrected temperature. Moreover, the GOP introduces correction factor square root 1 minus 2 MAP to the power of 2 alpha GOP that reduces the black hole's temperature, slowing its evaporation rate. This modification depends on generalized uncertainty principal parameters alpha GOP and the scalar particle mass MP emphasizes the quantum mechanic influence on the black hole thermodynamics, while the structural similarity of the two gravity theories results in analogous expressions for GOP corrected temperature and unmodified Hawking temperatures differs due to their dependence on the respective cosmological constants Im to the power of Fr and Im to the power of Ricci inverse. These findings highlight the potential for testing quantum gravitational theories to observations of black hole radiation spectra, bridging the gap between theoretical predictions and experimental constants. Figure 5 illustrates comparison of generalized uncertainty principle modify Hawking temperature for cylindrical black hole AFR gravity under the varying coupling constants alpha 2, alpha 3, alpha 4. The results highlight the quantum corrections to black hole evaporation rates induced by the generalized uncertainty parameter alpha GOP and the scalar parameter MAP variations in alpha 2, alpha 3, alpha 4 showcase significant deviation in Hawking temperature compared to general relativity black solid line, emphasizing the impact of higher order curvature terms in FR gravity. The plots are governed by equations 5.27 and 5.28. The mass parameters are chosen as m is equal to 1 and m is equal to zero point 0.1. Finally, we want to represent the GOP modifier entropy 99, 108, 111 of black holes, which can be derived by integrating the first law of black hole thermodynamics. ds is equal to dm divided by T generalized uncertainty principles. Figure 6 illustrates the effects of the GOP parameter alpha GOP and coupling constants alpha 2, beta 1, beta 2, and gamma on the modified Hawking temperature. T GOP to the power of Ricci inverse for cylindrical black holes in Ricci inverse gravity, the results are shown for two cases. Alpha GUP is equal to 0 classical scenario and alpha GUP is equal to 10 quantum gravity corrections. In general relativity limits, the Ricci inverse gravity parameters are set to 0. The Hawking temperature goes 0 as all approach 0. However, when Ricci inverse gravity is activated, the Hawking temperature remains finite as all tends to 0, signaling the possibility of remnant formation. Variations in alpha 2, beta 1, beta 2, and gamma reveal significant deviation from general relativity, emphasizes the role of Ricci inverse gravity corrections. The poles are governed by equations 5.27 and 5.28. The mass parameters are chosen as m is equal to 1 and mp is equal to zero point 0.1. And thank you so much for watching my tutorial video until the end. Today is the 12th day of June 2026. Time is 12 at 51 at morning.